Hey guys, working from home today, so wanted to show you my little puppies. Come here. Up. Don't you want to say hi? Come here. Here's Archie, and they were both just taking a nap, so they're a little bit sleepy. But this is Archie, and Daisy just went and laid down again, so I won't bug her. But whoa, love you too. Okay. There we go. Oh, that was the nicest thing. We can probably actually use this for our lesson today, if you'll let us borrow it. Bye. Okay. I just brought all my stuff home because I thought that would be, I don't know, just more fun with my dogs than at the school recording these. So today what we're gonna do in this video is gonna be notes number 20. Called emission spectra. Let me zoom in. Crunchy noises, sorry. You know it's really crunchy. So here, notes 20, emission spectra. And the cutouts that you're gonna want for today, we're not gonna use all the cutouts that I printed, but this one, I just keep this whole piece intact, just kind of cut that out. So this one, this one, this one, and this one. Is that all of them? 1, 2, 3, 4. Yep, okay. I think that's it. So give me a second to cut those out. The only downside from working from home is that I don't have all my markers that I'm used to. I love having all my markers. So this is the best I could find. It's this weird one from like IKEA. And it does like, it has 2 nubs. Oh, focus. Oh, there we go. So it's got like 2 nubs on it. And then when I write, it does this. Oh. So anyway, that's the best I can do for our title today. The title is Emission Spectra. And let me show you where the cutouts go. Okay, here's another kind of squishy notes page. But it's just going to be a lot better if we, just going to make that shiny. I don't want shiny tape. See, all these things I didn't think about when I was like, I'll just come home and do it. Like, I have shiny tape at home, but that's going to glare on the projector. So I'll get the dull tape out. It says this one says invisible. Right on invisible. Okay. It's from the 90s. So. See if it even sticks. That'll work. All right, so this is where they're all going. So pause the video and then rewatch once you've got them all situated. Okay. So here's the notes, and I actually, did my dog leave that bowl? Oh, he didn't. All right, fine. Let me go back a couple of pages here in the notes. And last time, one of the last times we talked about light, we were saying that when light comes in and strikes a metal surface, that metal surfaces do not hold on to their electrons very well. We know that that's just a characteristic of metals, right? They lose electrons. So the light comes in and the electrons go yeet off of the metal. That's one of the options that can occur when light strikes a surface. All right, I've drawn out the 2 options. Light can hit a metal surface, light hits metal, electrons go yeet off of the metal. That's option 1. We already did that. We called it the photoelectric effect. You don't need to write this down, just I'm writing it down on a scratch paper. paper. Okay, so photoelectric effect, we already did that one. This is the new stuff. When light hits other stuff that's not a metal. So down here, I'm going to draw an atom, and so here's going to be my nucleus. I really crappily drawn nucleus, where the protons and the neutrons are. We're not really worried about them, so I'm just going to kind of shelter them inside. That's our nucleus. We're not going to worry about it. Okay. Then a Bohr model of the atom. It has rings on it, and I'm not going to draw the full thing because then it would be too big for a piece of paper underneath the document camera. But you get the idea that these are the rings around the atom. Okay, the atom that I'm specifically talking about right now, let's just stick with the simplest one, and we'll say hydrogen. Hydrogen is the first, most simplest atom. It only has one electron. So I'm going to put that one electron here in ring 1. This is ring 1, 2, 3, 4, etc. So the light comes in. I'm gonna actually use a different color marker for the light. The light is yellow. It hit the metal and the electron went flying because metals do not hold on to their electrons very tightly. If we have light coming into this atom though, bam, it hits the electron. This atom holds on to its little electron baby so close, it doesn't want to lose it. So that energy, instead of making it fly off, maybe it bumps it up to like, whoop, ring 3 temporarily, but then it'll whoop, pull it back down. Does that make sense? So it's just kind of, it's getting hit with the energy and whoop, like flexing with it. So turning my camera around, instead of going yeet and like losing the electron, the light is coming in, the atom's holding the electron, and then it goes, and then back down. It raises it to level 3 or 4 or maybe 2 or wherever. It goes up a couple levels, holds it, and then down. It holds on to it. It kind of gets hit and then back down. That's the second option that occurs with nonmetals. This process has 2 names. When it goes up, because it's got that energy striking it, we're going to call that absorption. And then when it falls back down, we're going to call that emission. So this is just my scratch paper. This is literally just scratch paper. But you have a similar graphic in your notebook here. Absorption and emission. So I'm still going to use yellow for the light. I just realized the other day I had no idea. I thought that these pens, highlighters, like I've been using this side, I had no idea until a student showed me that I literally have like a marker on the other side. Okay, so we're going to use that one. So the light is coming in. When the electron is popped up from a lower energy ring to a higher energy ring, I'm going to show that it was here. It got moved and now it's currently, I'm going to draw it darker, see, before, after, whoop, moving up like that. It's absorbing energy. It stays there for a little while and then drops back down the same exact distance. And again, this little dot that's moving up and down is the electron. So I'm going to label it. Electron go up, whoop, electron go down, whoop. And the energy that was entering, energy is conserved. And as it falls, the electron is able to leave again. So this is just a mega flux of energy comes in. If it's absorbed, then released, then the amount comes out. The bigger the gap, let's see, I want a different color. I want my orange marker that I don't have, that I keep wanting. Oh well. The bigger the gap, the spacing, big space equals big energy. So that's what this triangle E is showing. The difference between here and here. The longer that this is, the more energy that the emitted light has. So if the energy comes in and only, here's the light, if it only goes boop, boop, that's a little energy. If the light comes in and it goes bing bong, then, sorry, Dewey, then the bigger that jump, the more energy comes out the other end. So it's just proportional. Don't overthink it. So on the side, in this little box, we'll put the following definition here. Entering light can be absorbed by the, this in quotes, ring system of the atom. Electron or electrons, but in this case just one, because it's hydrogen and it's the simplest element. Electron moves up to higher energy, higher energy ring or higher energy level. That's absorption. That's what happens when the light is being absorbed. It moves up. We don't really actually care about that part. Interestingly enough, we don't care about that at all, because the title of the page is called Emission Spectra. The one that we actually are going to be talking about from here on out is the emission spectra. What happens when the electron falls back down? That's pretty significant. So that'll be over here. When the electron, let's see if I can. When the electron falls, it's not really falling, right? But when it falls back down, comma, the distance that it fell corresponds to the amount of energy that is released. When the electron falls back down, the distance that it fell or falls corresponds to the amount of energy that is released. If this energy if this released energy, let me put that in parentheses here. If this released energy has a wavelength between 400 nanometers and 700 nanometers, we as humans can see it. And then draw an eyeball for fun. Here's my eyeball with some beautiful eyelashes. Sometimes the electron, when it falls, it makes not enough energy that we can see it, or too much energy that we can't see it. But there's this perfect little zone, and sometimes we can see it, and it's really, really cool. So the Bohr model for hydrogen, this is what I was drawing previously on my crumpled up piece of paper here, except for instead of a half ring, we've got the full ring. And I'm going to zoom in, crunchy noises, sorry. I'm going to zoom in as best as I can. I cannot seem to find this image in like higher resolution. I'm so sorry. But essentially, these are all of the different transitions that the electron can make in a hydrogen. Actually, on your homework, pause for a second, pull out homework 3.4. Go ahead and pause the video so you can see, because this one on the homework actually has a much, much higher quality image of what's actually going on here. It's showing, excuse me, the nucleus, ring 1, 2, 3, 4, 5, whatever, and it's showing electrons potentially could jump from ring 2 to 1, ring 3 to 1, 4 to 1, 5 to 1, 6 to 1. But maybe it drops from 3 to 2, or what is this, 4 to 2, 5 to 2, 6 to 2, and it's got all the different options for how an electron could fall. So I actually like this one better, but for the notes, we're going to use the kind of crappy, blurry version of that. So on the bottom, we've got part of the electromagnetic spectrum. This region here that's labeled is the IR. I'm going to relabel it infrared because it's already hard to read. So let's just write on top of that. This is infrared. We can't see that. It's too low of energy for us humans. The ultraviolet area is too high of energy for us humans to see. And then this magical little region here, the visible region that we do see, there are actually 4 transitions, 1, 2, 3, 4, that we can see. There are several transitions. See, this small distance, tiny distance, low energy, tiny distance, low energy, tiny distance, low energy. Can't see those. And the UV ones that are like ka-chow, 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 those really big, tall drops are too high of energy for us. So I'm going to do them in black because that's basically not a color. But the 4 colors that we can see are very specific. Red, purple, light blue and dark blue. So please, 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 please pause the video, go over to the pencil pouches, grab these colors or steal some from a neighbor, because these 4 colors are significant. I'm not just making this up. If you take a hydrogen atom and you electrocute it, give it electricity, these 4 colors will come off of the hydrogen. So it's very specific that you get a red, a light blue, a purple, and like navy blue. We'll come back to this picture. Scooting down here, this one lets you know which one's which. The 400 side of the electromagnetic spectrum, this is the purple stripe. The blue violet, or just I'd call it navy, is there. Bluish, greenish, lightish bluish, whatever. And the red. So this is an experiment that we can actually do, and I will probably do it with you guys once I'm back in person, but I'll show you some YouTube videos of it in the meantime. You take hydrogen gas, that's the one we've been talking about, hydrogen. Put it in a discharge tube, aka hook it up to electricity. Send it through a prism, kind of like that, what is it? Is it the Pink Floyd album art? Send it through a prism, and the hydrogen, because of the drops right here, we will see as red, light blue, dark blue, purple. So like red, light blue, dark blue, and purple. And what this picture is just showing that piece of paper here, but like cut out. Okay, so I'll zoom out so you can see both of these at the same time. These 4 drops, bam, 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 bam. I should have said bang, 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 bang. They're reversed on this picture. The 410 one is the purple one, which makes sense because it's the biggest drop. So that's going to be our highest energy color. Blue, light blue, and that baby jump is the 656 red. Just different artists' depictions depending on which way they wanted to flip the axis. Same though, right? While you've got those markers out, down here where it says hydrogen on the bottom, do the same thing, coloring in the lines. The one that's off to the side on its own, that's the red one. Then there's the light blue, the dark blue, and purple. All right, so even though we still have some empty spots here in the notes, we didn't talk about any other elements, we're just focusing on hydrogen right now, not worrying about helium, and something is going to go in this box here. But for right now, this is going to be the end of the notes for this video. And in the next video, we'll actually kind of analyze more instead of conceptually looking at the drops. We're going to mathematically look at the drops for hydrogen. So I don't want to do this next part with helium yet, because the whole homework 3.4 is on hydrogen. Does that make sense? Okay, so we're done with that notes for right now, but not completely.